Hello everybody, my name is Ricardo Borges. I'm the head of the Biodiversity Analysis and Evaluation Laboratory in the Baltimore's Institute of Research on Natural Products at the Federal University of Rio de Janeiro, Brazil. So in our laboratory, our goals revolve around the development of methods for compound identification within metabolomics and natural product research. For that, we focus on approaches such as dereplication, metabolomics, database access, isolation and purification, and cheminformatics for studies using different sources. Our main tools are mass spec, NMR, and bioassays, this last one with collaborators, for the final goal of understanding ecosystems and drug discovery. So in this video, I'm going to talk about the application of LipidXplorer to run knowledge-based dereplication of natural products. When I say knowledge-based, I'm referring to the fact that this application relies on the knowledge of fragmentation patterns for classes of natural products or other organic compounds. This is published in a series of 2 papers at Phytochemical Analysis at 2018. So this will be a tutorial for using LipidXplorer to achieve natural product dereplication using fragmentation pattern knowledge. To begin with, LipidXplorer is a GUI toolbox written in Python, mainly by this guy, Ronnie Herzog, in Max Planck Institute, designed to identify and quantify lipids for lipidomics using direct infusion mass spec. It makes use of expected variations of molecular formula for the precursor ion and for the fragments, rather than fixed values of molecular weights. By the end of the day, it can identify classes and subclasses of compounds and quantify them when quantitative protocol is used. So this is how LipidXplorer looks like. In this first window, we can use MZXML or MZML converted files under pick or central mode. Note that this can be the same file to be submitted into GNPS for molecular networking using the standard workflow. In this next window, we have to set the parameters to guarantee mass detection in both MS1 and MS2 with high accuracy. And in this final window, one must choose the MFQL files to be used and define the thresholds for both MS1 and MS2, considering expected shift from the exact mass. Well, the whole system depends on those MFQL files that are molecular formula query language. They are made of text files reflecting non-fragmentation patterns, so its flexibility is obvious. Thus, any molecule can be surveyed under this method once its fragmentation pattern is known or expected by comparison to a similar structure. This is what makes this method somehow database independent and promising for new compounds. So this is how the MFQL files look like. Note that each section has a title and a meaning to be explored. In this first active line, we have headings for the identification section at the final file, and it should represent the class or subclass for each specific designed MFQL entry. So the first section is used to define codes for the ranges of each detected molecular formula. The second, we specify the MS level where each code will be detected. The third one allows to create some kind of math rules to exclude false positives. And in the final fourth section, we define the results to be printed at the final CSV file. So this is an example of the molecular range. So range of atoms numbers and double bond ratio. Note the variation of the numbers of atoms and DBR, which is the double bond ratio. You have to define the polarity. Each code will be surveyed. So in this case, FA1 and FA2 are fragments from the precursor PRPE, here marked as MS1. So this third part enables to reduce false positive. This is quite useful. In here we are saying that the molecular formula of both fragments together must be equal to the precursor's molecular formula except for this fixed fragment. And in the final section we have entries in which each entry will be a column at the final CSV file. I suggest this section to be standardized for common headings in the final file to avoid confusion. So if you're planning to do some dozens of MFQL files, it's a good choice. It's a good practice to make those all the same. So in here we can see some codes written in the report part. So this is part of the language that was developed specific for the MFQL files, and it can be found on the LipidXplorer documentation under this QR code. So for this case specifically, we are using the code is PR. So you have pr.mass, pr.chemsk, or pr.intensity. And then you will print the molecular weight of the code of that ion, the PR, the molecular formula of that, and the intensity of the ion. So in here we have some examples of different MFQL files. So what do you need to start writing your own MFQL file? You need to define classes or subclasses. And for that, biosynthesis knowledge is essential, and fragmentation pattern should be previously established for each class or subclass. And you have to come up with rules to avoid or minimize false positive. That's the part that will require somewhat of creativity by the user, but these will allow for selectivity. So in this case, we have phenylpropanoids. Note that this fragment translates the characteristic loss of CO2. Note the variation of the hydroxy group from the minimum to the maximum structure. So in this other case, caffeoylkinic derivatives will be surveyed. This fragment translates the characteristic kinic acid as a fragment. And again, we are only considering variations on the number of hydroxy group in this specific MFQL file. In this other case, we have we have detection of monoglycosyl derivatives of steroidal alkaloids, epimenocholesterol specifically, and in this case we have possibility for acetylation. Note that the fragment that we are looking for is the aglycone itself, and the difference here in the headings of the report section, this difference will make it clear about the class of the monosaccharide in question. We can do that for monosaccharide, disaccharide, or trisaccharides, and so forth. So as an example, let's take it flavonoids. If you want to do an MFQL file for flavonoids, it will be too broad. The range of possible molecular formula will be too big. So it's a better choice to divide it into subclasses, such as hydroxy derivatives or methoxy derivatives, or glycosyl and hydroxy derivatives, or glycosyl and methoxy derivatives, and so on. So let's take it now for the hydroxy derivatives. We can draw the minimum molecular formula and the structural formula and the maximum structural formula and get the molecular formula for each. We make it explicit the possibility of a double bond in 2 and 3, between 2 and 3. And then we can write the section, the first section defining the code for this flavonoid subclass. Note the variations of the hydrogen due to the double bond ratio and the oxygen due to different oxygenation pattern. So for this third section, the such that section, this will not be very important for this specific case, but in essence, it would say that it must not have an extra carbon without an extra oxygen, and the other way around. That would be quite useful for methoxy groups, but this is not the case. So this will be the final MFQL file for this specific subclass of flavonoids, and this is not including fragmentation. This is only MS1 survey. Okay. Note that in the last section, the report section, it's important to think about well-thought codes that would enable users to come up with structural formula suggestions for each detected feature. So in this case, we are using the initial code for those flavonoids, following by the number of extra carbons, the number of extra double bonds, and the number of extra oxygens. So this would be an example of the output. So the system detected the method detected this mass, giving that error for that molecular formula, and this would be the code that will enable me to design to draw a tetrahydral flavone. I'm saying flavone for because of these extra double bond, and the only limitation is the limitation from mass spec that it will enable me to make sure of each substitution. So let's go further and add the fragmentation pattern. Here we add a typical fragment of flavonoids, the heterodiazolder fragment, and now we must add another code to be defined, and pointed out that it will be detected in the level 2. Thus, a new round of column headers should be added for printing. Here, users should plan to enable understanding of the fragmentation to aid structure identifications. Note that for a series of MFQL files, the report section should all be the same and in the same order to guarantee a common result. Here, each variable created is a column header. And using MS2 molecular formula restrictions cuts out a lot of false positive identification from the MS1 only. So a good example is these two new variables that we added to be created within the MSQL file. We intended to print out the mass difference and the molecular formula of the fragment between the precursor and its fragment ion. Parity will indicate the type of reaction, double bond cleavage or bond cleavage, or rearrangement and neutral loss. So to be a bit more detailed in this part, we have those codes percent 4.4F, percent 1.1F, and percent 2.2F. This stands for the printing 4, 1, and 2 respectively decimals in the value to be defined by the following term. And then this coding thing, percent %d to dot percent %d and percent %d can be modified as the user will, but these constructions will be completed by the value to be defined by the following terms between brackets. Here is an example for a methoxyflavone diglycoside using the identification of 3 signs, 1 precursor and 2 fragments. In this case, we didn't use the heterogeneous order fragmentation of flavonoids just because in our experimental data the aglycone shows itself like a base peak, so we didn't need to go further. So the resulted CSV file looks like this. Note the column headers and the first line after this. So each MFQL file used will generate a section like this. The idea is to enable information to be fast noted from the identified codes for precursors and its fragments. In this example, it's easy to annotate the presence of a deoxy exhaust and an exhaust, although users can and sometimes they should add neutral loss codes, but we didn't use those in here. Considering the perspectives for the use of LipidXplorer, I must stress the wide flexibility of the MFQL files. It is limited only by the user. For instance, we can use any range of molecular formula for both MS1 and MS2, and so any fragmentation reaction can be translated into these type of text files. Fundamental structure can be inspired from studies such as chemotaxonomic, um, genetic mining and biosynthesis, reaction products, metabolite products, and so on. One can probably write MFQL files to detect and identify any organic compound detectable through MS, and fragmentation patterns can be translated into them for false positive restrictions. Results produced here are not definitive, and the raw data must always be checked, but this is valid for all processing methods. And finally, merging LipidXplorer results with molecular networking, for example, GNPS's case, was proven to be promising in expanding compound identification. And as a result of all this, we published this first paper outlining this scheme for general database independent application of raw structs. And then we engaged to add our LipidXplorer approach to aid structure elucidation using molecular networking with GNPS. And we proved that the effect is impressive. Needless to say, each annotated node serves as a seed to propagate structural elucidation or even fine classification or other unknowns. And finally, we successfully applied this method using glycoalkaloids enriched fraction to detect more than 30 uh, similar structures accordingly. Thus, we updated the scheme merging GNPS's molecular network with the results from our LipidXplorer for database independent the application, and this is now routine in our lab. The main limitation though of LipidXplorer is the fact that it is designed for direct infusion, so it doesn't work with more than 5 minutes analysis. Users can import sections of 5 minutes, and maybe someone could try to modify the code for LCMSMS data. I would welcome it. So with this, I close this presentation, and I have to acknowledge people who have been helping me throughout this process and the next ones, actually. Thank you, everybody. And finally, thank you for your attention, and whatever critics or comments, feel free to contact me. I'm at the Federal University of Rio de Janeiro in Rio de Janeiro, Brazil, at the Institute of Research on Natural Products. Thank you. Bye.